Welcome to the topic 1.3 IEEE 754 representation in the series 1729 advanced topics. So this is part of section 1 floating point representation and I am Prabhunath. So in the previous discussion we had stopped here how to overcome the limitation of fixed point representation. So we were discussing on this and we also saw that for this beautiful problem there is an amazing solution also. Now to understand this scalability we will take an analogy here. Suppose there is a new rule enforced to construct a house within 6040 2400 square feet land area, and I have a wish of constructing a lavish villa of 10,000 square feet or even more. How do I achieve this? We have eating the same problem, right? Of course we will come out with the solution of this, get into a big house within the same area. So what is the parallel drawn for the scalability in the representation? Let us see the decimal representation that supports scaling of real numbers. Uh, just to recap on the fixed point representation, we have integer part and fractional parts. A quick recap of how this can be formed with the real number. We fix the width space for integer part and the fractional part. In this case it is 8 spaces. So we have 60 and 15. This is a notional decimal point or a radix point, right? Same thing with 8.2345. Here is an example. 8234.5. We come with an example with 8234.5, and the prominent number which is between 0 and 1 is 0.02. For every number we have a fixed width for integer part and the fractional part. The problem here is we are wasting space here. So how to conserve this space with the scaling, where the same space I will be able to represent huge numbers in terms of integers as well as in terms of the fractional part, right? The simple way is this 6.015. In this case, what are we doing? From the fixed point representation, we make the decimal point float, right? In this case, towards left. So when we make the decimal point floats towards the left, so does we increase or the exponent increases, right? The number of spaces it floats, the exponent increases by 1, right? In this case we also have a fixed width for integer part and the fractional part. Always the the width of integer will be only 1 digit space. That means the number which can be here is between 1 to base minus 1. In this case it is 1 to 9 or 1 to 10 minus 1 9, right? uh, we will see a next example. In this case there is no need for the decimal point to float. It will be fixed here, so it is 8.234 into 10 power 0. Next example, here we make the decimal or the radix point float 1 2 3. So when we make the decimal point float towards the left 3 times, we get exponent, we raise the exponent to 3 and the number becomes 234. You see we have fixed the fractional width space, that is 3 digit space. Next, the prominent figure between 0 and 1, we have a decimal point or radix point here. In this case we make the decimal point move towards right 1 and 2, it becomes 2.00, and the exponent value will be decremented as and when the decimal point floats towards the right. So generically, how can we represent this? It is I dot f into b par exponent. I is the integer part, f is a fractional part, b is the base, and e is the exponent. So do we gain everything from this representation? Nothing in this world comes for free. Scaling doesn't come free of cost. It's always at the cost of loss of precision. See what happened here. When I fix my width, field width for the fractional part 2, 3, 4, I am losing one some precision, right? Here in this case 8, 2, 3, 4. Again I am losing some precision here. So we have to accept this scaling with a pinch of salt. Pinch of salt will be the loss of precision, right? Next, we will look into the scaling of uh, real numbers in binary representation. How this representation supports scaling. Quickly, we will look into the fixed point representation of in the of the binary number. So we take example one which is greater than 1, and we take one more example which is between 0 and 1. See here 60.15, the corresponding fixed point representation 60 and 15, 0 0.02, 0 and zero point 0.2. In the next, this is the generic representation what we saw. Here we have the the decimal representation which supports scaling. Next is very interesting. We make the decimal point float 1, 2, 3, 4, 5 times to the left. Hence, we increase the exponent to 5. And here we have fixed the fractional width space to 8 bits. Hence, we have 1, 2, 3, 4, 5, 6, 7, 8. Right? We are losing these bits, right? We are paying the price on the loss of precision because of this representation which supports scaling. And see here, the beauty of this binary representation here is this space, as I told, integer space will occupy the number between 1 to base minus 1, 1 to 2 minus 1. It is always 1. This will be highly leveraged by the hardware designers when they implement this representation for calculating floating point numbers. We will see the number between 0 and 1. We make this point move towards the right. 1, 2, 3, 4, 5, 6. So when we move towards the right, why we are moving towards the right? Because we don't have anything on the left, right? So we get 1.01000 into 2 to the power of minus 6 because we have made the point float towards the right 6 times. And seldom we lose position when the number is between 0 and 1, but predominantly we lose the position when the number is more than 1. So this is one way of one of the representation, right, where in this case I have fixed the fractional part to be 8 bits, and the exponent value, seriously I have not fixed anything, but there is a standard which fixes this fractional part, which fixes the field width for exponential part, that we will see next. So the standard representation supporting scaling of real numbers, IEEE did this job of standardizing this idea to support scalability. It defined the width. It came up with two widths for storing fraction part or mantissa. One is 32-bit, one is single precision floating point number, one other is 64-bit floating point number. So in this of 32-bit, the fraction part is fixed, right? So apart from that, it standardized a lot of other important information in this representation. So the main thing we focus on this field width. So we'll look at the standard way of representation. Again, one is a sign number which we have not mentioned in the earlier slides. Okay, it's just about a magnitude. If yes is if the yes is 0, then it's a positive number. If it is 1, it is a negative number. So 1 point, yeah, again the standardization comes with the width here. So we'll quickly look into that. Reserved 8 bits for exponent, 1 bit for sign bit. Mantissa, the fraction part, for 23 bits, and 1 bit, what we were talking about, the integer part, it is assumed. The advantage, it leveraged the advantage of binary system. In binary system, the integer part will always be 1, unlike your decimal number system where the integer part will be from 1 to 9. So the designers leveraged this part and made it implicit. Now what is implicit here compared to fixed point representation? In the fixed point representation, only the decimal point or the radix point was assumed, but here both the integer part and the decimal part is assumed. That means there is no bit reserved for the integer part as well as the decimal part in this register or in this field width, right? Now next important point, exponent. I may have positive exponent, I may have negative exponent. Now how is that represented, right? The sign bit, the sign of the entire magnitude of this number is reserved, 1 bit is reserved for that. But again we have an exponent, positive exponent, negative exponent. Here it goes. Okay, the it uses XS127 format. It is just as simple as this. XS127 format means I have 8-bit reserved for the exponent. So I will say 127 I will consider it as 0, right? Anything above 127, 2 to 54, I'll take it as a positive exponent. That is what is XS127 format. So if the exponent field value is 128, that means my exponent value is 1. If the exponent field value is 127, the value is 0. If the exponent field value is 126, that means the exponent value is -1. So whatever the number you get, just if you want to find out the exponent from the available exponent field, you take the exponent field and subtract with -127, subtract with 127. Exponent field, subtraction with 127, you get the exponent value, right? Suppose if the exponent field value is 126, subtract with 127, 120, sorry, so subtract 127 from 126, 126 minus 127, which will yield to -1. If the exponent field value is 128, okay, you subtract 127 from 128, you get 1. This is what is all about XS127 format, which is used to store exponent field value. Please pay attention to the terminologies or words what I am using. Precise articulation will lead to minimal miscommunication. See a difference, exponent field value versus exponent value, right? Because we will be seeing this in our further discussions also. And again, I have just explained here, value 127 is considered exponent 0, and again value 0, exponent field value 0 and exponent field value 255 will represent special values, right? It is not considered under the normal values. And mantis, again, whatever we were discussing in the earlier slides, 1 bit implicit, which is not part of 32 bits, as well as the radix point. The same thing with the double precision, except for the width difference. I have 11 bits used to exponent, 1 bits for sign and mantissa. More precision you want, go for double precision representation, right? And again, the same details what you have here. We have excess. Oh, question mark. This is for you to figure it out. Yes, you please figure out all the question marks placed here. You need to figure out the value, right? And again, as I told, the IEEE not only standardized the field width, it standardized many other information, right? So these are the informations what you can find. If the exponent is 255 and the magnitude size is 0, then the value is positive infinity. If the exponent is 255, magnitude size is 0 and the magnitude is 0, then it is minus infinity. Like this, we have it as standardized lot of numbers. Same thing with double precision special cases that you will have to figure it out, right? I have given certain references which you can go through this, right? I think with this we will end this session. Hope you understood what is fixed point representation, as well what is how to scale for a fixed point representation, and how is that achieved through the IEEE 754 standard way of representing floating point numbers. Hence, the radix, since the radix point will be floating around, it termed it as floating point representation. With this, we will end this session. Thank you.